In this video, we're going to talk about the derivative sum rule. This video follows, this is the second video in a series, I should say. We talked about our derivative of a constant, derivative of a variable raised to a real number power, and then how we can deal with those terms when they have a constant multiple or a coefficient value. So basically, the derivative sum rule, that says that if we have two functions, which we can take the derivative of, two functions, u and b, differentiable functions of x, and it can be any variable as long as they're all in the same variable, right? A variable is a variable, it's just in how you interpret it. So u and v both are differentiable functions of x. Then their sum, we could have these 2, 3, 4, multiple, many terms, like a polynomial. Their sum is differentiable at every point where they are both differentiable. So, for example, the derivative of a sum, the derivative of this sum, u and v, right? So the derivative of u with respect to x is du dx. So I take the derivative of the first term, and the derivative of v, again with respect to x, is dv dx. So if we consider, and remember we know that we have our limit definition of a derivative. The limit is h approaches 0 of some function f of x plus h minus f of x divided by h. That's going to represent f prime of x. So I'm going to use my formal definition to show you or prove to you why this works. So I'm going to say here, let's find the derivative of the sum of these two differentiable functions, u being a function of x, and this could be plus or minus. Remember, addition is the same as subtraction. Subtraction is just adding the opposite number. So u of x plus v of x. And if I were to use my formal definition, taking the derivative of this, I would get the limit as h approaches 0. I'm going to plug x plus h in for both of those. So I've got u of x plus h plus v of x plus h. And that would be minus what we started with, which is u of x plus v of x. All of this now needs to be divided by h. So distributing, I'm going to rearrange my terms a little bit. I now have the limit as h approaches 0 of u of x plus h, that would be minus u of x, plus v of x plus h, and distributing that minus, I would get minus v of x. All of this is still over h. So I can think about this as like unadding these fractions, separating them. Here I would have the limit as h approaches 0 of this large quantity, u of x plus h minus u of x divided by h plus v of x plus h minus v of x divided by h. All right, so one thing that we know is the limit of the sum is the sum of the limits. So this is the same as then writing, I'm going to distribute, in a sense, my limit. The limit as h approaches 0 of u of x plus h minus u of x over h plus the limit as h approaches 0 of v of x plus h minus v of x over h. And so these both represent the definition of a derivative, right? The first one, that's the derivative, that's u prime of x. And our second one there, that represents v prime of x. And that notation there, that's the same as saying du dx plus dv dx. So I've shown to you why it is legal to take the derivative of the sum is the sum of the derivatives. All right, or rather what we had written up there, d dx of some u plus v quantity, that would be the derivative of the first term, derivative of u with respect to x, plus the derivative of v with respect to x. All right, so let's use this and then apply our rules from the previous video. So here we're going to find the derivative of the polynomial. Y equals 5x cubed minus 4/3 x squared plus 8x minus 10. I have 4 terms here, and they're all either added or subtracted from each other. We're asked to find the derivative. So considering this, the derivative of y with respect to x would be taking the derivative with respect to x of each term. So I have got 5x cubed plus the derivative with respect to x of negative 4/3 x squared plus the derivative with respect to x of 8x plus the derivative with respect to x of negative 10. Okay, so basically what we've just said is it's legal to take the derivative of each of these terms. So if we have lists of values that are all added or subtracted together, we can take the derivative of each one of those terms. All right, so I'm going to write this out a little bit differently. I'm going to go ahead and pull my constant multiple out for each one. So I'm potentially showing you more work than you need here, but I'm just trying to illustrate the rules. So I can pull that 5 out. For the next term, I can pull out negative 4/3. So then I have times the derivative with respect to x of x squared. I would have plus 8 if I factor that out, times the derivative with respect to x of x. And then this last one here, that's the derivative of a constant. I'm going to go ahead and write that as 0. The derivative of a constant is equal to 0. So now I have to use my power rule 1, 2, 3 times. And my power rule, remember, says the derivative of respect to x of x to the n, that would be n times x to the n minus 1. So I'm going to use that rule 3 times. My derivative here, I have 5. This becomes 3x to the 3 minus 1. 3 minus 1 is 2. Minus 4/3. Here I have 2x to the 2 minus 1. 2 minus 1 becomes 1, and we do not need to write 1. And plus 8. So now that x, notice we have a little invisible 1 power. That's like saying 1x to the 1 minus 1. 1 minus 1 gives us a 0. Anything to the 0th power is just going to be equal to that coefficient 1, right? X to the 0th power is 1, so it's like we have 1 times 1 here, which is just 1. And then, of course, I don't need to write this plus 0 any longer. It's gone. So my derivative here, dy dx, equals 15x squared minus 8/3 x plus 8. And so, again, let me just mention, I wrote that out way longer than one might write it after we've had a little bit of practice. All right, so I'm going to do one more example in this video, and I'm not going to write out as much work. So here again, we're going to find the derivative. So finding the derivative of f of x equals 2/3 x to the 5th minus 8x squared plus 13 over x cubed plus the 5th root of x squared plus 4,000. So I'm going to look at each of these as their own separate term. I'm going to take the derivative of each term. Now, before I do this, I notice I have some unusual, not exactly polynomial looking terms. Here I have x cubed in the denominator. Here I have a square root, a radical, which represents a 1/5 power. So before I even begin my calculus, I always try to rearrange using my algebra skills if possible. So I'm going to rewrite my function. This is still my original function. I'm going to use some color when I rewrite it. I have 2/3 x to the 5th minus 8x squared. Now 13 divided by x cubed is 13x to the negative 3. The 5th root of x squared, that becomes x squared. 5th root becomes a 1/5 power. So this is the same as writing x to the 2/5 power. And my last term there, I have plus 4,000. So this is still my original function. Now I'm going to take my derivative, and I'm going to write f prime of x. So I want you to notice the difference. This is my function. This represents my derivative. Remember, when we take the derivative, we always want to write that f prime first. So I'll take the derivative of each term. The first term, I'll leave my 2/3, and x to the 5th becomes 5x to the 4th. I have minus 8. X squared becomes 2x to the 1st plus 13. X to the negative 3 becomes negative 3x. Negative 3 minus 1 is negative 4. I have plus 2/5 x to the 2/5 minus 1. So 2/5 take away 1 is 2/5 take away 5/5, or negative 3/5. And this last term is a constant, so the derivative of that is plus 0, which I don't really need to write. So I have my function and now my derivative. I'm just going to clean this up. 2/3 times 5, that is 10/3 x to the 4th. 8 times 2, I'm going to have minus 16x to the 1st. I do not need to write that one. 13 times negative 3 is negative 39 x to the negative 4th. And I have plus 2/5 x to the negative 3/5. This is acceptable as an answer, but if you want to be very proper and clean this up, make it look like you originally started, you could go one step further. My first two terms, nothing would change there. But my 39, that could be negative or minus 39 over x to the 4th. And I could have plus 2 over 5x to the 3/5. And x to the 3/5, that's the same as writing the 5th root of 3. Right? So both these last two lines represent a correct derivative. All right, this one's just simplified, maybe to look a little bit more like what we started with. So at this point, you should have a clear understanding of how to take the derivative of anything that looks like a polynomial. It may not necessarily be a polynomial because a polynomial needs to have positive powers on each x. But if it looks like a polynomial, meaning you have a string of x's all raised to different powers, we can just use that power rule over and over and over again.